Welcome back to the channel. Today we're diving into a discovery that's sending shockwaves through astronomy. Observations of Andromeda's satellite galaxies are forcing us to rethink the very laws that govern the universe. Imagine rewriting the textbooks on gravity well. That might be exactly where we're headed. In this video, we'll explore what astronomers have found orbiting our nearest galactic neighbor, why it's so surprising, and what it could mean for everything from dark matter theories to the fate of cosmic structures. Stick around, because by the end you'll understand how a few distant star clusters might redefine physics as we know it. Andromeda, also known as M31, is a spiral galaxy roughly 2.5 million light-years from Earth and the largest member of our local group. Like the Milky Way, it hosts dozens of smaller satellite galaxies, compact assemblages of stars, gas, and dark matter bound by gravity. These satellites provide key insights into galaxy formation and evolution. Their distribution, motion, and mass profiles serve as laboratories for testing gravitational theories. Historically, astronomers have tracked their orbits to trace the dark matter halo enveloping Andromeda. Conventional models, rooted in Newtonian gravity and general relativity, predict how these small companions should orbit a massive host galaxy. Any deviation from these predictions could hint at new physics or require tweaks to existing laws. Until recently, Andromeda's satellites largely behaved as expected, validating decades of theoretical work. But a new analysis of their motions has revealed anomalies patterns that simply shouldn't exist under our current understanding of gravity, setting the stage for a revolutionary debate among astrophysicists. A team of researchers employed high-precision spectroscopy and deep imaging from powerful telescopes to measure the velocities and positions of Andromeda's faintest companions. By mapping radial velocities and proper motions, they charted detailed orbital paths for more than 30 satellites, unprecedented coverage. What they found was startling. Several satellites exhibit coherent motion in planes misaligned with the galaxy's disk, moving faster or slower than Newtonian predictions. One cluster, dubbed M31b Frone, seems to be on a trajectory nearly perpendicular to Andromeda's rotation, defying expectations. Even more puzzling, the velocity dispersion among inner satellites was far lower than models predicted, indicating a gravitational pull that standard dark matter halos can't explain. These measurements are statistically robust, with uncertainties under 5% ruling out observational error. Could these patterns arise from past galactic mergers or tidal interactions? The researchers argue no. Simulations show that such interactions would produce temporary, chaotic streams, not the long-lived, coherent motions observed. The conclusion? Something fundamental about how gravity operates on these scales might be off. The anomalies among Andromeda's satellites are more than curiosities, they strike at the heart of gravitational theory. Newton's inverse square law and Einstein's general relativity have passed every test in the solar system and beyond. Yet here we see behavior that demands an explanation. One proposition is modified Newtonian dynamics, MOND, which adjusts gravitational acceleration at extremely low values. In MOND, gravity's pull weakens more gradually than Newton predicts, potentially accounting for the slower motions of Andromeda's inner satellites. However, MOND struggles to explain the perpendicular orbits without adding ad hoc tweaks. Other theorists suggest a new long-range force or a different distribution of dark matter, perhaps ultralight fuzzy dark matter, that forms wave-like structures altering gravitational potentials on kiloparsec scales. If confirmed, these findings would necessitate recalibrating mass estimates for galaxies across the cosmos and revising cosmological simulations. The stakes are astronomical. Rewriting gravity could reshape our understanding of black holes, cosmic expansion, and even the ultimate fate of the universe. Dark matter has been the go-to solution for galactic anomalies since its proposal nearly a century ago. It explains flat galactic rotation curves and large-scale structure formation. But Andromeda's satellites may demand a more complex picture. If dark matter halos aren't smoothly spherical, but contain clumps or wave patterns, satellite motions would deviate from smooth orbits. Alternatively, if dark matter interacts with itself or with normal matter in unknown ways, it could create gravitational ripples around galaxies. These ripples might manifest as the coherent planes and velocity dispersions we observe. Cosmologists must now ask, are these features unique to Andromeda or widespread across galaxies? Surveys of the Milky Way's own satellites and other nearby galaxies will be critical. If similar anomalies appear elsewhere, the evidence for exotic dark matter or modified gravity grows stronger. On the flip side, if Andromeda remains an outlier, astrophysicists may need to investigate its specific merger history or unseen baryonic structures. Either way, our cosmic map and history could undergo a major revision. To resolve these mysteries, astronomers are planning extensive follow-up campaigns. Next-generation observatories like the James Webb Space Telescope and the Extremely Large Telescope will measure proper motions with micro-arcsecond precision, refining orbital models. Radio arrays, such as the Square Kilometer Array, will probe hydrogen gas around satellites, seeking signs of past interactions. On the theoretical front, computational astrophysicists are running high-resolution simulations incorporating alternative gravity laws and exotic dark matter candidates. These virtual galaxies will be compared against Andromeda's real satellite system to evaluate different scenarios. Collaborative efforts across observational and theoretical domains are essential, combining precise data with sophisticated models. The coming decade promises to be transformative. We may uncover new particles, revise fundamental physics, or confirm that our current laws are more robust than we dared hope. Stay tuned, because as more data arrives, we'll inch closer to answering one of the most profound questions in science. How does gravity truly govern the universe? The observations surrounding Andromeda's satellites urge us to reevaluate the very nature of gravity. Classical mechanics, as outlined by Newton, work exceptionally well at the scale of the solar system. Einstein's general relativity expanded this by showing how massive bodies warp space-time. But neither can easily explain the behavior of galaxies on the cosmic scale, especially without invoking dark matter. With Andromeda's satellites moving in strange alignments and speeds, it's possible that our existing gravitational models are only approximations of a more complex underlying truth. Some physicists propose emergent gravity theories, where gravity isn't a fundamental force, but a result of thermodynamic principles or quantum entanglement on a cosmic scale. These radical ideas may seem far-fetched now, but so did black holes when they were first proposed. If these new gravitational models can successfully explain the anomalies observed in Andromeda's satellites without invoking unseen matter, they could mark the next step in our scientific evolution. Modified Newtonian dynamics, or MOND, has long been a fringe alternative to the dark matter hypothesis. It suggests that Newton's laws need a revision at very low accelerations, like those seen in galactic outskirts or in faint satellite galaxies. An MOND gravitational attraction drops off more slowly than Newton would predict. This could explain why the satellites of Andromeda move the way they do without the need for invisible dark matter. In light of the new satellite observations, MOND is gaining fresh attention. Its proponents argue that the behavior of Andromeda's satellites fits better with MOND than with standard cold dark matter models. However, MOND struggles with other large-scale cosmic phenomena such as galaxy cluster dynamics and cosmic microwave background patterns. Still, the new findings are pushing some astrophysicists to consider hybrid models blending aspects of MOND with elements of traditional physics. If Andromeda is MOND's smoking gun, we may be on the cusp of a paradigm shift in cosmology. One intriguing explanation for some of Andromeda's strange satellites is the concept of tidal dwarf galaxies. These are galaxies formed not from dark matter halos, but from material stripped away during galactic collisions. When two galaxies interact, Gravitational forces can pull gas, dust, and stars into long tails, and these can coalesce into small galaxies. If Andromeda underwent a past collision or merger, it could have created tidal dwarfs that now orbit as satellites. These objects wouldn't behave like traditional dark matter-dominated galaxies. Their odd orbits and low-velocity dispersions could match what's observed. The catch? Tidal dwarfs are supposed to be short-lived or unstable in long-term orbits, and the regularity seen in Andromeda satellites suggests long-standing, coherent systems. Nevertheless, this hypothesis reminds us that galaxy evolution is messy and non-linear, and sometimes the strangest answers come from the most dynamic cosmic events. The stellar halo of Andromeda contains scars from its violent past streams of stars, from cannibalized galaxies, remnants of ancient mergers, and disturbed gas clouds. These features suggest Andromeda has had a more active merger history than the Milky Way. Could these past events explain the satellite anomalies? Possibly. A merger could create coherent orbital planes if the incoming galaxy's satellites remained intact. Additionally, the redistribution of dark matter and baryonic matter during a merger could lead to gravitational irregularities that influence satellite motion. Simulations show that satellites from a fallen galaxy can remain in a disk-like structure for billions of years. If Andromeda swallowed such a system, it could explain the polar alignment of many of its current satellites. But even this explanation doesn't fully account for the unexpectedly low-velocity dispersions. It's likely that mergers are part of the answer, but not the full story. What makes the Andromeda discovery more compelling is that it's not the only galaxy with strange satellite alignments. The Milky Way also has a vast polar structure, its own satellites orbit in a thin, extended plane. Other galaxies, like Centaurus AE, exhibit similar features. This pattern suggests that such planar structures may not be rare quirks, but a common, yet poorly understood phenomenon. Standard cosmological simulations predict that satellites should form a roughly spherical halo, not thin disks. The repeated appearance of these planes challenges the validity of those simulations or the assumptions they're based on. If these structures are truly ubiquitous, they may indicate a flaw in our current dark matter-based models. Alternatively, it could mean that satellite galaxy formation is more influenced by large-scale cosmic filaments than previously thought, funneling matter into preferred orbital paths. Whatever the case, Andromeda is now a centerpiece in a much larger mystery. To truly change the laws of gravity, we must understand how gravity works at the smallest scales at the quantum level. Quantum gravity aims to unify general relativity and quantum mechanics, but it remains one of physics' greatest challenges. The anomalies in Andromeda's satellites might, indirectly, hint at a deeper gravitational mechanism, one that operates according to principles we've only scratched the surface of. Theories like string theory, loop quantum gravity, and causal dynamical triangulations propose frameworks where space-time itself is emergent or discrete at tiny scales. If gravity arises from quantum information or is shaped by extra dimensions, it could behave unexpectedly at larger scales too. Perhaps what we're seeing in Andromeda is the large-scale signature of quantum effects, or the evidence that gravity is not as continuous and smooth as Einstein envisioned. Though speculative, this line of thought opens the door to a revolution that could unify the fundamental forces. Satellite galaxies aren't just pretty clusters of stars orbiting their hosts. They're crucial for testing cosmological models. Their motions, compositions, and interactions provide insight into the distribution of dark matter, the formation of galaxies, and the structure of the universe itself. In the lambda, cold dark matter, CDM model, large galaxies are surrounded by thousands of subhalos, many of which should host satellites. But we observe far fewer satellites than predicted, a problem known as the missing satellites problem. Andromeda's newly observed anomalies deepen this mystery. If satellites aren't behaving as expected, it could imply flaws in how we simulate cosmic evolution. This makes satellite galaxies invaluable testbeds for refining or rewriting our models. Every new discovery about these small companions could have universe-wide implications. And as Andromeda shows, the smallest galaxies might contain the biggest secrets. The European Space Agency's Gaia mission has transformed our understanding of galactic dynamics. Gaia's unprecedented catalog of stellar positions and motions allows astronomers to track the movements of stars and galaxies with exquisite precision. Its data has helped identify streams, mergers, and orbital planes in the Milky Way, and it's now being applied to Andromeda. While Gaia can't resolve individual stars in Andromeda like it does in our galaxy, its proper motion measurements for brighter objects, combined with Hubble data, offer critical clues about satellite trajectories. These precise motions are what uncovered the anomalies in satellite velocities. Without Gaia, this revolution in galactic kinematics wouldn't be possible. The mission continues to refine our understanding of stellar dynamics and may provide the datasets that finally settle the debate over gravity and dark matter. Here's a wild thought. If gravity behaves differently on galactic scales, what does that mean for future space travel? In the distant future, as humanity explores beyond our solar system, an accurate model of gravity will be essential for navigation. Spacecraft traveling at relativistic speeds or navigating intergalactic space will need predictive models that reflect real cosmic dynamics. If Andromeda's anomalies lead to a revision of gravitational laws, it could impact how we plan deep space trajectories, interpret cosmic signals, and design propulsion systems. This isn't just academic, it's foundational knowledge for any civilization aspiring to explore the stars. Andromeda might be telling us not just about galaxies, but about the roadmaps we'll one day use to reach them. When scientific paradigms shift, they often come with deep philosophical implications. If the laws of gravity are shown to be incomplete or inaccurate, we must re-examine our place in the universe. For centuries, gravity was seen as a fixed, universal constant, a reliable force that held the cosmos together. Changing that understanding introduces uncertainty, but also possibility. Could the universe be more flexible, more dynamic than we thought? Could life and structure arise in ways we've never imagined? Andromeda's satellites, in their quiet, distant orbits, may be whispering truths about a cosmos far stranger and more beautiful than we ever dared dream. While Andromeda is in the spotlight, our own Milky Way hosts similar oddities. Several of its satellite galaxies, like the Large and Small Magellanic Clouds, don't behave as traditional models expect. Some move in a near-disk formation, and others appear gravitationally bound to each other rather than to the Milky Way. Like Andromeda, our galaxy also shows evidence of a vast polar structure where many satellites lie along a thin plane. These similarities strengthen the case that what's happening in Andromeda isn't an anomaly, but part of a universal pattern. If both major galaxies in our local group display the same contradictions, the models used to describe them likely need adjustment. This makes the case stronger for systemic reevaluation of galactic dynamics, and not just an isolated rethink for Andromeda alone. The question now is, are these features cosmic coincidences, or signatures of a deeper rule in galactic architecture? Galaxies are not scattered randomly across the universe. They're woven into a massive web of dark matter and gas known as the cosmic web. These filaments act as highways for matter, funneling it into dense regions where galaxies form and grow. New studies suggest that satellite galaxies may follow these filaments and enter host galaxies like Andromeda and the Milky Way in pre-aligned structures. This could explain the planar arrangements we observe. In this view, the odd satellite alignments aren't a failure of our models, but a reflection of the large-scale structure of the universe itself. If satellites are delivered in groups along filaments, their unusual motion patterns would make perfect sense. It's a beautiful theory because it links the smallest visible galaxies to the largest invisible structures. Confirming it, however, requires simulations of much higher resolution and scope than what's currently typical, something the next decade of cosmological modeling may finally deliver. Believe it or not, these tiny satellite galaxies may function as cosmic dark matter detectors. Since they're mostly composed of dark matter, or so the theory goes, they respond sensitively to the gravitational environment around them. When satellites move in ways we don't expect, it may indicate the presence of exotic dark matter behavior or unseen substructures. For instance, if dark matter forms clumps or waves, these can disturb a satellite's orbit. If Andromeda's satellites are truly acting strangely, perhaps they're dancing to the rhythm of an unseen dark matter symphony. Some physicists are even experimenting with models where dark matter interacts through forces beyond gravity, like self-interaction or decay. These new types of dark matter could subtly change how galaxies evolve, and satellite galaxies might be the only visible signposts of such physics. Andromeda's anomalies may ultimately help us see the invisible matter that shapes our cosmos. As data from satellites like Hubble, Gaia, and JWST pours in, processing and interpreting it becomes a monumental task. That's where AI comes in. Machine learning algorithms are now being trained to identify orbital patterns, classify galaxy types, and even predict missing satellites based on dark matter distributions. AI has already found galaxy mergers and structures that human researchers missed,